We looked at the symmetries of several different solids in an earlier television program. The program concentrated on the regular tetrahedron and represented each symmetry as a permutation of the vertices. The group of all such permutations, S4, has 24 elements, and in fact all 24 arise from symmetries of the tetrahedron. In general, with n symbols, there are n factorial permutations. And the group Sn is very rich in subgroups. Even S4 has 30 subgroups, whilst S5 has well over 100. In this program, we'll show you how various groups can be represented as subgroups of Sn. In fact, by the end of the program, we'll see if there are any finite groups which cannot be represented in this way.
To get an insight into the algebraic ideas we'll need later, let's start with another solid. It's just a double tetrahedron. We're going to represent its symmetry group in several different ways. For example, we'll represent the symmetries algebraically as permutations of the 5 vertices. But to do that, we must first look at the symmetries geometrically. Remember what a symmetry is. It's a geometrical transformation, such as a rotation or reflection, which leaves the object occupying its original position. To help us find these transformations, let's quickly count how many of them there are. That is, how many different orientations are there which this object can end up in? We can use the triangular cross-section as a reference. We'll keep the triangle superimposed and fixed in space. That way, as I move the object, we'll keep track of its original position in space. Here's one new orientation. Here's a second. And now we're back to where we started. So that's 3. But there are 3 more orientations upside down. 4, 5, 6. These 6 are all the orientations which are physically possible for this object. But in counting symmetries, we mustn't forget reflections. So let's imagine a reflected version of this object. So here's the reflected version, and this also has 6 different orientations. 1, 2, 3, then upside down, and another 3. So that's 12 different orientations, 6 for the original object and 6 for the reflected version. Now, how are these achieved geometrically? Well, for these 6 orientations, we need direct symmetries. But where are the axes of rotation? And for these 6, we need indirect symmetries, but where are the planes of reflection? The colors will help you see where the vertices go. Again, let's superimpose our reference triangle. And let's start with rotations. There's a vertical axis of rotational symmetry through the top and bottom vertices. And you've already seen that we can rotate through 2 pi by 3, 1/3 of a revolution. Or through 2/3 of a revolution. And a further third of a revolution brings us back to where we started. That accounts for 3 direct symmetries, including the identity. What about other axes of rotation? There's this horizontal one through the blue vertex. And this time we need a rotation through pi, half a revolution. And if we do it again, we get back to where we started. And in fact, there are 2 more axes like this. So these 4 axes of rotation account for all 6 direct symmetries. What about the planes of reflection? Well, you've seen one already, through the 3 central vertices. What about other planes? In fact, there are just 3. There's this vertical plane, again passing through 3 vertices. And there are 2 other vertical planes. So, there are just 4 planes of reflection. But where did the other 2 indirect symmetries come from?
Well, here are the 4 types of symmetries we found. The composition of 2 symmetries also gives a symmetry. And in fact, one of the missing indirect symmetries is obtained by composing this reflection with the third of a revolution about this vertical axis. There's no single plane of reflection, it's a composition of a reflection with a rotation. And for the final indirect symmetry, just compose this reflection with 2/3 of a revolution. We can see why those compositions are the missing 2 once we represent all 12 symmetries as permutations of the 5 vertices. Let's first take this vertical axis. If I rotate 1/3 of a revolution, 2π/3, then the vertices on the central triangle have moved from their initial positions. Let's record where they've moved. The vertex in position 1 goes to position 2, vertex 2 goes to position 3, and vertex 3 goes to position 1. Vertices 4 and 5 stay put. We normally omit the arrows and write the permutation like this. There's also a shorthand way of writing this in cycle form. This notation records the fact that symbol 1 goes to 2. Then we look at 2 and record the fact that it goes to 3. And the way we interpret the last symbol in the cycle is that it goes to the first position, which is what happens. Symbol 3 goes to 1. So our permutation can be expressed as a 3 cycle. Symbols 4 and 5 stay fixed. This can be recorded in the form of 1 cycles, but usually we take fixed symbols as understood and leave them out of the cycle form. So that's one of our 12 symmetries, expressed as a permutation of the 5 vertices. Let's now look at a reflection. This one. Vertices 3, 4 and 5 are fixed because the plane passes through them. And vertices 1 and 2, well, they just interchange their positions. So in cycle form, we get a 2 cycle. So that's 2 symmetries. I don't need to look one by one at the other 10 because there's a quick way of working out all 12. This relies on the fact that they all leave the triangular cross-section occupying its original space. In other words, each of our 3-dimensional symmetries performs a symmetry on the 2-dimensional triangle. In fact, all 6 symmetries of the triangle are performed. Remember what they are. The identity, 3 reflections, and 2 rotations. In fact, these 6 cycle forms also represent 6 of our 12 3-dimensional symmetries. That's because the center of rotation corresponds to an axis of rotational symmetry. And if we look at the reflective symmetries, then each vertical plane of reflection gives a line of reflection for the central triangle. Now, these cycle forms don't include the symbols 4 and 5, because the symmetries that they represent keep vertices 4 and 5 fixed. There are 6 other symmetries which affect the triangular cross-section in exactly the same way, but which do move vertices 4 and 5. To find these symmetries, first reflect in the horizontal plane. This interchanges vertices 4 and 5. Now compose this reflection with each of the symmetries we've found already. So that's 12 distinct permutations of the 5 vertices, representing our 12 symmetries. But what do these last 6 look like geometrically? We know the first one is reflection in the horizontal plane. The next one is actually a rotation. It's the rotation through pi about this axis. 4 and 5 are interchanged, and so are 1 and 2. But vertex 3 is fixed. Then we get rotation about a second horizontal axis, and about a third one. And finally, the last 2 are the indirect symmetries, which are not simple reflections. Each is the composition of this reflection with one of the 2 rotations about the vertical axis. We can now use the permutations to discover facts about the geometrical group. For instance, suppose we want to determine the composition of this rotation followed by this one. Well, rather than stretching our visual imagination, let's just compose the corresponding permutations. Where does the symbol 1 go? Under this permutation, 1 goes to 2, and then this one takes 2 to 3. So in the composition, 1 goes via 2 to 3. Now look at 3. This permutation leaves 3 fixed, and this one takes 3 to 1. So the composition takes 3 to 1. Now look at 2. It goes to 1 here, then 1 goes back to 2. So the composition fixes 2, and we don't need to write it down. Next, 4. Well, both 4 and 5 are unaffected by this permutation, so they're just interchanged by this first one. And that does it. 1 and 3 are interchanged, and 4 and 5 are interchanged. That's a rotation about this horizontal axis. So working with the permutations can certainly assist our geometrical visualization. Let's now look more closely at the permutations themselves. They form a subgroup of S5. It's a group in its own right, but it's essentially the same as our geometrical group of symmetries. In other words, the permutations compose in exactly the same way as the corresponding geometrical transformations. We say the 2 groups are isomorphic.
Now let's go on to consider several different representations of the symmetry group. First, an easy modification. What happens if we label the vertices differently? For instance, let's interchange labels 2 and 5. Well, we then have to interchange 2's and 5's wherever they occur. So we end up with a different subgroup of S5. But of course, it's still isomorphic to the geometrical group of symmetries. And different labellings of the vertices give yet more subgroups of S5, each isomorphic to the symmetry group. Well, that was a simple modification. Here's a more interesting one. Label the 6 faces. Then we can represent each symmetry as the permutation of the numbers 1 to 6. For example, rotation in the vertical axis by 2 pi by 3 takes face 1 to position 2, face 2 to position 3, and face 3 to position 1. And similarly for faces 4, 5, and 6. So the rotation is represented by a pair of 3 cycles. What about reflection in the horizontal plane? The faces interchange in pairs. 1 and 4 interchange, 2 and 5 interchange, and at the back, 3 and 6 interchange. So with this representation, we'll get a subgroup of S6. Here are the 2 we just found. As a matter of fact, we don't need the numbers here. We could just use the colours instead. Each element is still a permutation of 6 symbols. 6 colours in this case, but any 6 symbols will do. It's still a subgroup of S6, and it's isomorphic to our geometrical symmetry group. So, we're able to represent our symmetry group in several ways. As a subgroup of S5, as a different subgroup of S5, and as a subgroup of S6. In fact, we can even represent it as a subgroup of S9. There are 9 edges, so we could look at how each symmetry permutes these 9 edges. So, our symmetry group can be represented by lots of different permutation groups, and we could do the same for other objects.
In fact, permutation groups arise so naturally, you might start to wonder whether they arise naturally for other kinds of groups as well as symmetry groups. For example, suppose we're given an abstract group consisting of 6 elements, and all we know about it is its Cayley table. So we know how the group elements combine. For example, element X composed with element V gives element W. Can this group be represented as a group of permutations? Well, there's a way of associating a permutation with each element. Take X, for example, and consider its row. We can think of this as a list of 6 symbols and regard it as a permutation of the column headings. And in cycle form, this permutation turns out to be a product of 3 transpositions. So for each element of our group, we can associate a permutation in this way. Here's another example. This time, from element V, we get a product of 3 cycles. And for the identity element E, we get the identity permutation. And so on. In the end, from the 6 rows of the table, we get these 6 permutations. Each permutes 6 symbols, so is an element of S6. Let's call each one by the corresponding capital letter. Now, do these 6 permutations form a group, and is it isomorphic to our original group? The answer is yes. To see this, let's just investigate closure. For closure, we have to establish that the composition of any 2 of the permutations gives another one of the 6. Let's try an example. Permutation X, composed with permutation V, turns out to be this permutation. And this is indeed one of the 6. But look what else has happened. If we look at the corresponding elements of our original group, we find they combine in exactly the same way as the permutations. X composed with V equals W. Well, this is not an isolated case. It turns out to be true for every pair of elements. That is, the 6 permutations combine in exactly the same way as the corresponding elements of the original group. In other words, the Cayley table for the permutations is essentially the one we started with. All you have to do is replace the letters of the original group by the capital letters of the corresponding permutations. So these permutations form a group which is isomorphic to the original group. That method of associating a permutation with a group element was devised by the English mathematician Arthur Cayley, and his theorem holds for every finite group. The proof is quite easy. Take any finite group G. With each element little g, we associate the permutation given by its row in the Cayley table. Well, what are the elements in its row? They're compositions. So the permutation we get from little g is this one. We'll call this permutation PG. We get a unique permutation in this way for each element of the group. Now, how do these permutations combine? A general element x is mapped by pH to hx. But hx is an element of the group, so it appears somewhere in the top row of the permutation PG. And it's mapped by PG to the element g times hx. So in the composition, x is mapped to g times hx, which is the same as gh times x by associativity. So PG combined with pH is the permutation obtained by multiplying everything on the left by gh. That is, it's PGH, the permutation associated with the element gh. And that's all we need. The permutations combine in the same way as the corresponding elements of the original group G. So the set of permutations is a group isomorphic to the original group. Well, Cayley's theorem suggests that we'll know all about the structure of any finite group once we know all about permutation groups, that is, subgroups of Sn. In a sense, this is true, but even for relatively small values of n, Sn is a large and complicated group, so understanding its subgroups is no mean task. In fact, unsolved problems concerning permutation groups still abound and will continue to fascinate mathematicians for some time to come.